Howdy, welcome to Elementary Statistics. I am Lance Curtis. This is the lecture for section 8.3, testing a claim about a mean. Here in this lecture, we're going to talk about hypothesis testing as it applies to means. So just as we saw with confidence intervals, there are times when we don't know the population standard deviation and times when we do, and the test statistic, as we'll see, that we calculate is going to be different in each of those cases. We'll talk about how to conduct mean hypothesis testing in StatCrunch. We'll also look at calculating critical values in StatCrunch and conclude with a brief look at using confidence intervals on the mean for resolving hypothesis testing. So in this section, we're going to present methods for testing a claim about a population mean. Now, as with the confidence intervals about a population mean, the key question here is the same. Do we know what the population standard deviation is? If the answer to that question is yes, then we're going to use the standard normal distribution and we'll calculate a z-score for our test statistic. However, that's very rare. It's more common for us not to know what the population standard deviation is, in which case we'll use the student t-distribution and calculate a t-score for our test statistic. Now, as we saw with confidence intervals, again, knowing the population standard deviation is very rare in practice. So let's look first at the case where we don't know what sigma is, because this is by far the most common case. We have to meet two requirements in order to use our methodology here. The first requirement is that we have a simple random sample. The second requirement is that the population must be normally distributed or have a sample size greater than 30. This allows us, the sample size greater than 30 allows us, per the central limit theorem, to use a normal distribution as an approximation. If we're already normally distributed, then we don't have to worry about sample size. So, because we don't know what the population standard deviation is, our test score will be a t-statistic. And this is the formula used for calculating that t-score. Now, as we saw before with proportion hypothesis testing, the more traditional methodologies will use either a p-value or a critical value in order to decide the test. Let's look at an example to illustrate how this works. So we have a table here of values of radiation emissions in units of watts per kilogram from a sample of 11 cell phones. Use a 5% level of significance to test the claim that cell phones have a mean radiation level less than 1 watt per kilogram. And then we're given some summary statistics. So we have a sample. The mean of the sample is 0.938. The sample standard deviation, 0.423. Before we can actually get into the hypothesis test, we have to check to make sure our requirements are met. So we're assuming the sample is a simple random sample, simply because we don't have any evidence to the contrary. We don't have any evidence that suggests it's not a simple random sample, so we just go ahead and assume that it likely is a simple random sample. Our sample size is less than 30, so we have to check to make sure that we're normally distributed. We can't assume per central limit theorem that we have a normal distribution of our data. So we have to check for normality, and we're going to do that with the QQ plots that we were making earlier in the course. When we do, we get a plot that looks something like this. And yeah, the lines are more or less close to that red line that you see there in the middle. And there's no sinusoidal pattern. There's no obvious huge departures from that line. So we're going to say that, yeah, the data appears to be normally distributed. So we have that requirement met. And what that means is that both our requirements are met, so we can proceed with our hypothesis test. First, we express the claim in symbolic notation. So cell phones have a mean radiation level less than 1 watt per kilogram. So that symbolically, we can write that as mu is less than 1 watt per kilogram. Next, we write our hypotheses. So first we're going to start with the null hypothesis, which, remember, the null hypothesis is always a statement of equality. Then the alternative hypothesis typically reflects the claim. So in this case, we just take that symbolic notation for the claim and we turn that into our alternative hypothesis. So here are our hypotheses you see on the screen. Mu equals 1 for the null hypothesis. Mu is less than 1 for the alternative. Now, as declared in the problem statement, we have a significance level alpha of 5%. Because the claim is about a population mean, the most relevant statistic to this test is the sample mean, x bar. Why is that? Well, because remember, the mean is an unbiased estimator. So the sample mean will target the population mean. This makes it the most relevant statistic for this test. So let's go ahead and calculate our test statistic. Here's the equation that we use. We substitute values into this equation. So we were given our sample mean of 0.938. We're going to just assume that the null hypothesis is true. That means that we're assuming that the population mean is actually equal to 1. So we're going to substitute that in there at the top. And then in the bottom of our fraction, we were given the sample standard deviation, 0.423, and we divide it by the square root of our sample size, which is 11. We punch this out on our calculator, and out comes negative 0.486. This is our test statistic. We're now ready to decide our test. So we can use the p-value and compare it with the significance level alpha. So here we're comparing areas. If the area for the p-value can fit inside the area for alpha, then we're going to reject the null hypothesis. Alternatively, if that's not the case, then we fail to reject the null hypothesis. Now the p-value is the area under the curve that's bounded by the test statistic, which we just calculated on the previous slide. So in our t-calculator, we put in negative 0.486, and we're looking to the area to the left of that test statistic because our alternative hypothesis was less than. We hit compute and out pops the area under that curve, which is the p-value, 0.3187. So 0.3187 is much larger than our alpha of 5%. Therefore, we fail to reject H0. The area for the p-value is larger than the area for the alpha. We can't fit it in. Therefore, we fail to reject H0. We're outside the rejection region. Now, alternatively, we can compare the test statistic with the critical value to get the same result. Our critical value is negative 1.812. So again, if we put the area for our alpha into our calculator, the 5%, and then look for the horizontal value that bounds that area, that's going to be our critical value, which is negative 1.812. Because our test statistic is greater, the test statistic is, so that's -4, is that right? Yeah, negative 0.4. I was getting confused looking at the -4, but it's negative 0.4. So negative 0.4 is outside our rejection region. Therefore, we fail to reject H0. Now, because we're failing to reject the null hypothesis, we conclude there is not sufficient evidence. And we're going to say that it's not sufficient evidence to support the claim because we have a one-tailed test. So there is not sufficient evidence to support the claim that cell phones have a mean radiation level less than 1 watt per kilogram. Now, when the standard deviation for the population is known, we're going to use a test that involves the standard normal distribution to calculate a z-score. In reality, it's very rare for this to happen because if you know what the population standard deviation is, which is rare in itself, it'd be even more rare for you not to know what the population mean is. So why would you be conducting a hypothesis test on the population mean when you already know what it is? So it's very rare for us to actually encounter this situation. However, once in a blue moon, things do happen, stars do align, and you get out the need to calculate a z-score instead of a t-score. So when that actually happens, here's the equation you're going to be using. Notice how this equation is very similar to the one that was used to calculate the z-score. The big difference is that we're using the population standard deviation instead of the sample standard deviation to calculate our test statistic. Let's look at the previous example that we just went through about radiation emissions from cell phones. Suppose that we know that the population standard deviation is 0.480 watts per kilogram. This is not going to change the null or alternative hypothesis, so those are going to stay the same. However, the values that we use for comparison to decide our test, those values will change. So we need to calculate a new test statistic. We have a z-score now instead of a t-score, which we calculate with this formula here. So we plug in the values that we have, and out comes negative 0.428. Slightly different from what we had before. This new test statistic means that we have a new p-value. Okay, remember the p-value is the area under the curve that's bounded by the test statistic. So now we have a new area under the curve because we have a new boundary for that area in the test statistic. So now we have 0.3343 for a p-value. Using the standard normal distribution instead of the student t distribution means we have a new critical value, which you can put that in your calculator to confirm. It's going to be negative 1.645. And so with these new values, we can make new comparisons, but we're going to reach the same conclusion that we did previously. Our p-value is greater than our alpha. So therefore, we're outside the rejection region, and we fail to reject H0. Alternatively, we have a test statistic that is outside the rejection region of the that's bounded by the critical value, and so therefore we're going to fail to reject H0. Let's take a look at mean hypothesis testing in StatCrunch. Just as we saw with proportions, you're going to be using the same menu options to test the mean for a hypothesis testing as you did with the confidence intervals back in Chapter 7. So the same menu options are going to be used. Typically, you're going to select one sample with summary. For some of your homework problems, you may find that you actually are given an actual data set. In that case, you want to select with data instead of with summary. But for the most part, you're just going to be using the same menu options that you did with confidence intervals. Now, sometimes in the midst of a problem on hypothesis testing, you're going to be asked to find a critical value. StatCrunch makes this very easy for one-tailed tests. You can also use this for two-tailed tests, which we'll get to in a moment. First, let's look at the one-tailed test. So, in the event of a one-tailed test, for most problems, you're not going to know what sigma is. Therefore, you're going to want to use your t calculator. Enter the degrees of freedom and the significance level alpha as you see here. So degrees of freedom go on the top. Remember, That's 1 less than the sample size. Significance level alpha is the area under the curve, so that's going to go to the right of the equal sign in your probability calculation. Make sure you match the inequality symbol in the drop-down menu with the inequality symbol from your alternative hypothesis. Make sure those two match. And once you've got all that, you hit compute. And then you just read the critical value right from that's the horizontal axis value there to the left of the equal sign in your probability calculation. For a two-tailed test, you need to make some minor adjustments. So first we're going to select the between option there at the top of our calculator. Now, when we do this, StatCrunch is going to calculate the area in between the tails. So this is fine. We're looking for critical values. We want the values that are bounding the tail regions because that's the region of rejection. So this will give us those critical values. But we have to remember that the area that's calculated is the area between the tails. So first we enter our degrees of freedom, 1 less than the sample size. And then we're going to take the complement of our alpha. Because the alpha, remember, is the area in the tails. But the between option in the StatCrunch calculator is calculating the area in between the tails. So you have to take the complement. Take 1 minus your alpha level and put that in for the area to the right of the equal sign in your probability calculation. Once you do that, you hit compute and out pops your two critical values. Notice that you essentially have the same number, just one's positive and one's negative, and this is because the t-distribution is symmetric about the mean. Let's look at another example to illustrate what we've learned so far. Discarded plastic for 1 week from 62 randomly selected households were weighed, and we found that the mean weight was 1.911 pounds and the standard deviation was 1.065 pounds. This is for the sample. Now we're asked to answer the following questions with respect to the claim that the mean weight of discarded plastic is greater than 1.8 pounds. First, what are our hypotheses? Second, what is the test statistic? Third, what is the p-value? Fourth, use a 5% significance level to decide whether to reject the null hypothesis. And 5, what do you conclude from the hypothesis test? So let's take these questions one at a time. First, what are our hypotheses? Well, the first thing you want to do is think of the claim that's being made. Identify the claim. So from the problem statement, we see that the mean weight is greater than 1.8 pounds. So that's going to be written symbolically as mu is greater than 1.8. Remember, the null hypothesis is by definition a statement of equality. So we're going to set mu equal to that claimed value of 1.8. Then the alternative hypothesis typically will directly reflect the claim. In this case, we just take the claim and we're just going to turn that into our alternative hypothesis. So mu is greater than 1.8. Notice that we match our inequality signs. So because the claim is directly reflected in the alternative hypothesis, we have a one-tailed test. And this one-tailed test is a right-tailed test because we're using the greater than inequality sign in our alternative hypothesis. It's like an arrowhead pointing in the direction of the critical region. So here, the greater than sign points to the right, so therefore we have a right-tailed test. Now, the second question was, what is the test statistic? So in StatCrunch, we just simply use our menu options, go to Stat, T-Stats, one sample, with summary, because we weren't given an actual data set, but we were given summary statistics. In the options window, enter in those summary statistics, and then make sure that the hypothesis test area matches the hypothesis that you actually created previously. So we'll put our claimed value in for that first window, 1.8, and then make sure that from the drop down on the inequality sign in the alternative hypothesis that it matches. Press compute when you're done, and then in the results window you can read the test statistic right off the results window. The test statistic will always be the second to last value in the results table. So the second to last value is your test statistic. The third question is, what is the p-value? Well, we can get the p-value by reading right off the results window. It's always the last value listed there in the results window. So the last value is the p-value. The next to last value is our test statistic. Now, the fourth question asked us to decide whether to reject the null hypothesis. Well, we're going to compare p-values with an alpha level. So our p-value, if the area for our p-value is greater than the area for our alpha, then that means we're outside the rejection region and we fail to reject H0. However, if we can fit the area for the p-value inside the area for alpha, we're inside the rejection region and therefore we reject H0. Let's look back at our results window again. The p-value is the last value there listed in the results window. So a p-value of 0.2075 is greater than our alpha of 0.05. Therefore, we're outside the rejection region and we fail to reject H0. What then do we conclude from our hypothesis test? This is the last question we were asked. So typically with these questions, you're given 4 options like the ones you see here on the screen. If you compare the options, you'll see that there's only 2 main differences between them. The first is at the very beginning, you either have sufficient evidence or you do not have sufficient evidence. If you reject H0, you have sufficient evidence. If you fail to reject H0, you do not have sufficient evidence. We fail to reject H0 in this example. Therefore, we want the correct answer is going to start off by saying there is not sufficient evidence. So the answer is going to be either A or B. We don't need to look any further at C or D. Comparing A and B, you see that the difference between those two answers is that A says warrant rejection of the claim, whereas B says support the claim. How do we know which one to pick? Well, do we have a one-tailed test or a two-tailed test? We had a one-tailed test. Therefore, for a one-tailed test, you want to say support the claim. And therefore, the answer option is answer B. If we had a two-tailed test, then we would have picked answer A, which says warrant rejection of the claim. So, when we have a one-tailed test, our alternative hypothesis will directly reflect the claim behind the test. And in that case, you always want to conclude that you have evidence to support the claim. You're talking about evidence to support the claim. Now, if you reject H0, you have sufficient evidence. If you fail to reject H0, you have insufficient evidence, or you do not have sufficient evidence. Let's look at one more example to make sure that we understand this process thoroughly. A study checked 20 randomly selected students and found their mean time to graduate from college was 6.5 years, with a standard deviation of 3.506 years. Answer the following questions with respect to the claim that the mean time to graduate is 4 years. Notice we have the same 5 questions from the previous example. So again, let's look at these one at a time. The first question we're asked is, what are our hypotheses? Well, first think about the claim that's being made. Identify the claim. What is the claim? The claim is that the mean time to graduate is 4 years. So that means the mean time to graduate is exactly 4 years, or mu equals 4. Remember, the null hypothesis is by definition a statement of equality. So we're going to write mu equals 4 as our null hypothesis. Typically, the alternative hypothesis directly reflects the claim. In this case, that's not going to happen because the claim symbolically is represented in the null hypothesis, not the alternative. And why is it in the null hypothesis? Because statements of equality are, by definition, belonging to the null hypothesis. That's what the null hypothesis is. That's how it's defined. So any statement of equality goes with the null hypothesis. What then do we write for our alternative hypothesis? Well, the alternative to being equal to is going to be the complement of being equal to, which is being not equal to. So our alternative hypothesis is going to say mu is not equal to 4. Again, we cannot directly reflect the claim in the alternative hypothesis in this case because the claim is one of equality, and statements of equality go with the null hypothesis. Now, we don't have a match between the inequality sign for the alternative hypothesis with what is represented in the claim. Therefore, what we have is a two-tailed test. Let's look at the next question we were asked. What is the test statistic? Again, we're going to go to the same menu options that we did previously in StatCrunch. Stat, T-stats, one sample with summary. In our options window, we're going to put in the summary statistics that we were given, make sure that our hypothesis test area matches what we had previously written down for our hypotheses, and then we press compute. The test statistics we read right off the results window. So the test statistic is going to be the next to last value in our results window. The third question we were asked is, what is the p-value? This is always the last value listed in the results window. Decide whether to reject the null hypothesis. Well, we can do this one of two ways. We can look at it by comparing a p-value with an alpha to see if we're inside or outside the rejection region. So go back to our results window, we look at our p-value, and we see that it's 0.0048. 0.0048 is less than 0.05. Therefore, the area for our p-value can fit inside the area for our rejection region. Therefore, we reject H0. What do you conclude from the hypothesis test? Well, again, here we have the same 4 options in the wording of our conclusion. So we're going to go through the same process that we did previously. First, did we fail to reject H0 or did we reject H0? In this instance, we rejected H0. Therefore, there is sufficient evidence. So we're not going to look at answers A and B. We're going to look at C and D. The correct answer is either C or D. Now, comparing C and D, we see that the difference between them is one says support the claim, that's answer option C, and the other says warrant rejection of the claim, that's answer option D. Which do we pick? Well, do we have a one-tailed test or a two-tailed test? Remember from the beginning of the problem, we determined that we had a two-tailed test. Therefore, we're going to look in terms of warranting rejection of the claim, and the correct answer option we select is answer option D. There is sufficient evidence because we rejected H0, and we're warranting rejection of the claim because we have a two-tailed test. So, when our alternative hypothesis is not a reflection of the claim, we have a two-tailed test. And therefore, we're going to conclude that we're warranting rejection of the claim. If we have sufficient evidence, that means we've rejected H0. However, if we do not have sufficient evidence, then that means we failed to reject H0. Let's take one little look at confidence intervals on the mean before we wrap up today's lecture. So earlier when we looked at population hypothesis testing, we saw that confidence intervals didn't always come out with the same result as the formal hypothesis testing methods that we just talked about. This is not true when you're looking at hypothesis testing on a population mean. So confidence intervals are just as reliable when you're testing a claim about a mean as the more traditional methods of using a comparison of a p-value with an alpha level or a comparison of a test statistic with a critical value. Confidence levels of a confidence interval will be the complement of the significance level alpha for a hypothesis test. So if we want to conduct a hypothesis test at, say, the 5% level, then we need a confidence level for a confidence interval of 95%. So whereas alpha is representing the area in the tails, the confidence level for a confidence interval is the area in between the tails. So alpha level of 5% corresponds with a confidence level for a confidence interval of 95%. An alpha level of 1% corresponds with a confidence level of 99% for a confidence interval. So on and so forth. So we can actually use a confidence interval to determine the result for a hypothesis test. That brings us to the end of this lecture. If you have any questions, you know what to do. Otherwise, I will see you in class or the next video. Thanks for watching.